Welcome everyone, and thank you for joining us. This is our fifth session for this program. Actually, no, sixth session for this program. And this is actually my last session doing this series. I'm very excited to have my guest today and to take you all and to continue this journey for the latest scientific research done in the UAE. The guests that we had during this journey are all distinguished scientists and researchers from the Mohammed Rashid Academy of Scientists. They have had great impact to their research field, whether it's nationally or internationally. And my guest today, I'm also much more excited about because his research field is more unique in the UAE, and I have not met anyone who actually does similar research before. So I'm as excited as all of you today attending to learn more about this topic. I would like to welcome Dr. David Holland. Thank you for joining us. Dr. David Holland is a professor of mathematics at the Center of Atmospherics Ocean Science. And also he's affiliate faculty and principal investigator. So he's the PI at the Center of, for Sea Level Change. Welcome, Dr. David.
Thank you very much, Amal. It's great to be here. Good afternoon to you and good morning from Canada.
Yeah, so Dr. David, maybe before we start, maybe it would be great or exciting to tell our guests today, our students today, where you are and what are you working on?
Is it possible we could share the screen? I could just show you where I am.
Yes, please go ahead.
Okay, so let's try that. So can you see my Earth?
Yes, we can see the Earth.
Okay, so today, because of the virus, normally I would be in New York City here at NYU, but I have quarantined to this small island of Newfoundland off Canada. So I'm in a very small town here, and I'll probably be here for quite a while. Normally, at this time of the year in the summer, I would be further north in Greenland studying the ice sheet.
Yeah.
This is the most northerly NYU Abu Dhabi campus is in Greenland. If you ever get a chance to go up there, or if you have been, you'll know how beautiful it is. In the other summer, I work on the other end of the world in Antarctica, down yonder. And Antarctica last year was successful. This year, Antarctica is closed. Typically, we would take 1,000 people to Antarctica. This year, to our research site, it'll be 4 people, and maybe they'll make it, maybe they won't. And so that's where I am today.
Wow, that's amazing. I have so many questions just about that location by itself. But maybe before we go into the presentation, so you work in the climate change on oceans and how the atmosphere work. Can you maybe tell us a story about you in research that maybe told you or made you feel that yes, this is why I decided to go into this field, to inspire today's students or future scientists?
Right. Well, so my own story of how I ended up doing what I'm doing today, like all trajectories, it's full of twists and turns, but there are some common themes. So I grew up as a child here in Canada. I was always interested in nature and natural science. In Canada, it's cold, and so there's a lot of ice and snow about half of the year. So I always grew up interested in ice and snow. But I also grew up interested in the physical environment, the physics of it, and through that, also in mathematics. So it's kind of that combination where mathematics, physics, and an interest in nature and ice came together. And so when I attended university, that was kind of the path that I forged for myself. I did my PhD at McGill University in Montreal in Canada. That was a very rich and enlivening experience. I studied theoretical and computer modeling, and then I started my career with NYU, and then a decade ago, I joined NYU Abu Dhabi And I've been pursuing this line of research since.
That's amazing. And I think everyone here is actually excited to learn maybe more about that. So I think that's a good place for us maybe to start to learn about today's subject, which is the science of climate change. We can start from here. The floor is yours, Dr.
Okay, so would you like to start the presentation now?
Yes, please feel free.
Yeah, okay. So let me bring that up. So share screen. And let's see, bring this up. Okay, and Amal, you can just interrupt and ask questions where clarification is needed, so we keep it relevant. Great. Okay, so this presentation is about the science of climate change. There's also the policy of climate change, which is another half of the story, which we are not addressing today, equally important, but today we're talking about the science part of it. The geographical context for my science is this idea that the Earth itself is a very small place. And currently we have 2 ice sheets. Normally we have 3. NYU in New York City, for those of you who've been to New York City, is in this location in Greenwich Village. It's a lovely campus in New York City. The glaciers that we are studying for climate change, the first one is the Greenland ice sheet, which survived the last ice age. And in particular, we're studying Jacobs Harbor, Jakobshavn in Greenland. It's a World UNESCO Heritage Site. It's an amazingly beautiful place, large icebergs, bigger than city blocks or parts of cities. In Antarctica, what we are studying and focusing on climate change is Western Antarctica. All of the ice you see is below sea level. It's already in the ocean and it's melting rapidly in a glacier that's about to become very famous, Thwaites Glacier. You will hear much about that in the coming decades. And so where you all are, or many of you are in the UAE. NYU also has a campus constructed maybe 5 years ago or more now on Saadiyat Island. It's a very beautiful campus, very nice architecture. And that's my home for kind of half of the year, and the other half is in New York. So the talk is in 4 parts. The first is our climate system. What is the climate system? The second part is the climate of the distant past. Here I'm thinking back to the beginning of the formation of the Earth up to more recent times. And then we'll also zoom into what I call the recent past, which is the part since humans have been having an impact on climate, which is really the last 100 or so years. And finally, what will be our future climate? And clearly, that's in part up to us. And we'll see what might be in store for us.
Atlanta, Houston, if that's not the Earth, we're in trouble. That's the Earth, and we have a very good view of it today. There are a few more cloud bands on than yesterday when we beamed down to you, but it's a beautiful sight.
So that I remember as a child seeing that on television, and to say the least, it blew me away. And that's when I first thought of the Earth, as a kid, as something that is something. I didn't have the word climate system, but I knew it was something like that. And so I was really interested in how does this thing work, and how does it fit into the bigger picture in our solar system. So if we zoom in on the Earth and we look at the pieces of the climate system, the first thing that grabs our attention is the atmosphere, which we now live in. And it's a very thin layer of gas, and it contains a little bit of carbon dioxide, 1 part or 400 parts per million. And it's the change in that gas concentration that really is the focus of modern climate change. Going back through eons and eons, carbon dioxide has changed by enormous amounts, high and low. And what's unique about today's situation is that it's changing very rapidly, and almost certainly due to human influence. And that thin layer you're looking at, that blue veil of gas, is effectively a blanket. And we are making the blanket thicker or warmer, and that will have some consequences. And that's well-established physics. Beneath the blanket of air is a blanket of water. Water covers more than 2/3 of our planet. It's really a blue planet. And the water is also affected by the air and the carbon dioxide. In fact, the ocean holds 1,000 times or more the amount of carbon dioxide. So when you think of the ocean, it's not only water and something that's warming, it's a vast reservoir of carbon dioxide. Most of the carbon dioxide, or a lot of it, is in the ocean as compared to the air. And so the ocean is a very large buffer. And not so obvious from these pictures is what is it that the ocean and the atmosphere are doing in the climate system. And it's really quite straightforward. The sun imports heat to our planet in the tropical equatorial region, and the atmosphere and ocean move that heat to the polar regions. That's effectively what's happening. It looks a little bit more complicated because we are spinning, and so you see all these highs and lows as air spins. But forget about the spin. It's just our planet moves heat from one region to another. That's the actual climate system. And as we change the atmospheric composition, the way it does that will change. Hence, we use the word climate change. So some places will become warmer, some colder, et cetera, et cetera. But overall, we can expect change. The land is a big player. You can see here from the vegetation, parts of the Earth that are covered in ice, Greenland and Antarctica, parts that are covered in vegetation, green, and parts that are desert. And this is intimately tied up with our atmospheric circulation. The atmosphere has 3 circulation cells, one of them operating in the equatorial region, has a descending branch in the 30° south, 30° north, and hence you can see desert regions there where air is basically descending, and where it's rising in the tropics, you can see it's green and a lot of rain. And it's the kind of shifting of those belts of rainfall that are of current great interest. The other part of the cryosphere is the so-called cryosphere, or the ice. This is a view from the Galileo spacecraft as it left Earth decades ago, and it took this final snap, kind of a picture, a selfie of Earth, if you will. And there's the Antarctic ice sheet, this vast amount of ice. Most of the fresh water on Earth is stored here. This has enormous potential to change global sea level by tens and tens of meters. Currently, the part we are studying appears to be unstable, and we see this from satellites in space and whatnot. And around the Antarctic ice sheet, and which is the focus here, is some thinner ice called sea ice, and that's also undergoing some change. So jumping to the distant past climate, so the Earth apparently formed more than 4 billion years ago. And since that time, the climate, if you will, has changed dramatically, including periods of time when apparently Earth was completely encased in ice, the so-called snowball Earth, which may have happened just before the most recent outbreak of life, some 560 million years ago. Thinking about the UAE in particular, if we're really going to look back at climate change, this is one good example. If we look back just past the Cambrian to the Precambrian, and you follow this is the Arabian plate, and you can see Abu Dhabi's in where the mouse is. Amal, can you see my mouse? Yeah. So, great. And so you can kind of follow through time to this last 600 million years, or last 10% of the Earth's time. As the Arabian plate moved, it actually left the equator and it was hanging out in the southern hemisphere for a while. Then it did a 180 and flipped itself around, and then it traveled back north again, up around with the dinosaurs at 165 million. And that's kind of where it is today. So that's dramatic climate change that has happened in the UAE over time. Zooming to a closer period of time, for the last 2 million years, we've really entered a sequence of ice ages where most of the time we have more ice on Earth than now. Right now is an interglacial, and there's only Greenland and Antarctic ice sheets hanging around. Typically here in Canada, I would be under an ice sheet most of the time. New York City would be under an ice sheet, Canada, the United Kingdom. In the Persian Gulf, there would be no Persian Gulf, no Arabian Gulf, because sea level was some 100 meters lower in order to build these huge ice sheets. The Gulf is only at most, I believe, less than 100 meters. So it would have been completely dry for most of the time in the past 2 million years. And so again, these are natural cycles of climate change, and they're driven by the fact that the sun and the earth orbit and the distance changes. And as the sun and earth become further apart, earth becomes colder. And that's also tied in with carbon dioxide, which we will come back to. This is kind of zooming even to more recent time. Here we can see the flooding of the Gulf. 14,000 years ago through the Straits of Hormuz, we can begin to see some water showing up. 10,000, 8,000, and around 6,000 years ago, it's pretty much looking like it is today. Some of the islands are tall enough or high enough to still survive. The last time I was in the UAE, my wife and I went to Sirbani Yaz Island, beautiful little island off the coast to the southwest of Abu Dhabi. So that's kind of the past, that climate has changed, and that will continue into the far future. The real question we have at the present is now that there are closing in on 7, 8, 9 billion of us, we seem to be having a large impact on our limited space on planet and our resources, our atmosphere and ocean. And that really started with the Industrial Revolution just over 100 years ago. It's evident in data from air temperature. If we look at these anomalies, which is the difference from the average, we really see that the planet has been warming, and mostly in the polar regions and particularly in the Arctic. And scientifically or theoretically, we actually expect the greatest warming in the Arctic, because as you melt ice, which is white and reflects heat to space, you replace it with blue ocean, and blue ocean absorbs more heat. And so you get what you expect. And we've seen this very large rise in air temperature over the Arctic. And that's a threat in the polar regions because that's where all the ice is located. Anything is possible. It could be that all of this is a statistical fluke. You can never be certain about anything. However, it is very, very suspicious that the trends that we see, and that the past decade was the hottest on record. So it's yes, you're never certain, but this looks very much like a real trend. And the trend that's caused by a change in carbon dioxide, which is almost certainly a contribution from humans. And so as we go into that, I want to jump a little bit for the next two slides to my research, which is focused on ice on the planet. And as I said, we have 2 ice sheets at present, one in the north, one in the south. And so last summer, my team from Abu Dhabi and New York were in Greenland, and then we went to Antarctica. And I think the easiest way to share that is we took international media with us, and to share with you a few minutes of each of those, you get a sense of what is it the research we're doing. And the research is driven by the graph you're looking at, the fact that it's becoming so warm in the north and now in the south that the ice there is under threat. And that will have a global impact on sea level. So let's jump to that.
You're looking at the White House where minutes ago, the Trump administration announced it will be setting a national standard for fuel economy in cars and trucks. Now, this move targets California and will essentially environmentalists. In our Eye on Earth series, CBS This Morning is showcasing original reporting focusing on the health of our planet. Greenland's melting ice sheet is contributing to a rise in sea levels that could threaten millions in low-lying areas. The situation became more urgent this summer when 11 billion tons of surface ice melted in just one day. Seth Stone visited Greenland's glaciers to meet some of the scientists on the front lines of climate change.
Icebergs broken off glaciers fill fjords. Ice melting here in Greenland is affecting sea levels around the world. In fact, if all of Greenland's ice sheet melted, sea levels could rise by 23 feet worldwide. We choppered out to Helheim Glacier, which holds enough frozen water to fill the entire state of Pennsylvania a foot deep. You can see the camp now. Scientists are perched at the glacier's edge. Among them, NYU's David Holland and his wife Denise, who manages logistics.
People say follow the money. Well, this is a story really about follow the warm water. Water melts ice quicker than air, and so the ocean can melt this ice sheet much faster than the air.
Denise Holland took this video showing a giant piece of Helheim Glacier breaking off or calving last summer. The ice chunk was so big it could stretch from lower Manhattan to Midtown in New York City.
It was huge chunks, small chunks, everything just broke apart in this one big jumble of ice.
This is a radar detector. Holland and the NYU team set up radar equipment that peers into the glacier to measure its movement and thickness. The icy surface is deceiving. One comes up here and doesn't see a problem.
Right. And so the potential problem is when we put our probes down in this fjord, down to the bottom, and we detect large volumes of very warm, salty water.
Because you know that could melt the ice out.
Yeah, and that's not sustainable.
Greenland's ice sheet shed around 11 billion tons of surface ice in just one day in August. That's enough to fill around 4.4 million Olympic-sized swimming pools. The mayor of coastal Kurusuk, Greenland, says they're feeling climate change with more ferocious storms.
How's this nice?
Because of this extreme weather, because of the wind.
Because of strong wind.
And nearby in the picturesque port town of Tasiilaq, this is all Inuit culture.
This is all Inuit
Rasmus
culture.
Paulson took freelance work at this museum of Inuit culture. His winter sport adventure business had a shorter season.
Last year was extremely good. We had a lot of snow, a lot of ice. We were able to do dog sledding all the way into the first week of June. This year I had to close down my business for winter activities in the middle of April.
Summer came sooner.
Summer came very, very much sooner.
Coming off the ice sheet in winter.
At the glacier, David Holland and his team have been surprised to learn just how finicky the atmosphere is.
People say climate will change by a degree or something. In the tropics, I don't think that matters. But when you're at the freezing point, minus a half degree below is freezing, plus half degree above is melting. 1 degree is everything.
They're collecting data to understand what is happening. The scientists can then tackle the question, why? For CBS This Morning, Seth Stone, Helheim Glacier, Greenland.
Doing good work out there on today's CBS This Morning podcast. Seth and his producer share details of their reporting from Greenland, including what locals say about the effects of climate change. And to learn more about what you can do to help the environment, and everybody can do something, we invite you to go to our CBS This Morning Instagram page for advice from teen climate activists, Greta Thunberg and others. Greta, you know, was here at the table the other day.
Well, she's at Congress.
Yes, she was.
So that part is what's happening in the north with Greenland. Greenland is where some 50,000 people live on the island of Greenland, which is connected to Denmark in a government sense. You can see that there's big impacts on the people living there in terms of the fisheries are changing, their way of life is changing, their habitat. So there's change is neither good nor bad, it's change, and people have to deal with it. If we turn to the south, the story becomes far more dramatic in that the volumes of ice in Antarctica are enormous, and what we're seeing there happening presently unfold is not a good sign. So we just returned from there a few months ago, and we had to bring our own media team because we had limited capability. But nonetheless, here's a report from PBS.
The Thwaites Glacier is one of the largest in Antarctica, and it is melting at an alarming rate. The world took notice earlier this month when temperatures there hit nearly 70 degrees. But getting a better read on what's happening has been a challenge. Our science correspondent Miles O'Brien gave scientist David Holland and his team camera equipment to document their mission to the glacier. Miles has this dispatch as part of our series, The Leading Edge.
It's an urgent scientific mission at the far edge of what's possible, to the edge of a massive melting glacier. It's the largest, most menacing source of rising sea levels all over the world. Welcome to the Thwaites Glacier in West Antarctica. Our guide on this journey is David Holland, a professor of math and atmosphere ocean science at New York University. He is a principal investigator on the MELT project, part of the International Thwaites Glacier Collaboration. The 5-year campaign is funded by the UK Natural Environment Research Council and the US National Science Foundation, a NewsHour funder as well. Why is Thwaites so important? Why is it worth the effort?
So it's the most vulnerable place on Earth. And the curious thing is, how is it that it's so vulnerable and at the same time it has warm water in front of it today? I mean, there's two things that may be coincidental, but they're both real and they're happening.
For years, scientists have warily watched Thwaites from afar using NASA satellites. About the size of Florida, it is vanishing at an alarming rate, retreating about a half mile and thinning as much as 15 feet every year. It sits on land below sea level. There is nothing to stop its accelerating retreat. It could melt away in a few decades. Some call it the Doomsday Glacier.
If Thwaites were to melt or drop into the sea tomorrow,
How much sea level rise would we expect?
so it's less than a meter, it's probably of order of say 65 centimeters, then the neighboring ice would become unstable. And so altogether it'd be more than 3 meters of ice, something, 10 feet. It's a major change, a rewriting of the coastline.
Thwaites is like a cork in a bottle. Once it is gone, there will be nothing to stop a cascading loss of nearly all the glaciers in West Antarctica. That is why Holland wanted to come to this place, to drill a half-mile hole through the ice to see what's happening underneath. It's never been done before, and it very nearly did not happen this Antarctic summer.
The motto for me is have no expectations. If you have expectations, you will be deeply disappointed.
In November, they flew to Christchurch, New Zealand. Within a few days, they were on a U.S. Air Force Air Mobility Command C-17, stuffed to the gills with scientists, support crews, and gear. After a 5-hour-long flight due south 2,300 miles, they landed at McMurdo Station, headquarters for the National Science Foundation in Antarctica. But they were still more than 1,300 difficult miles away from their camp on Thwaites, and the weather was terrible, and the airplanes kept breaking down. What was to be a 1-week stop in McMurdo for briefings, training, and practice became more than a month. By the time they got to Thwaites, all the weather and mechanical trouble left them barely enough time to do their science. But safety first. A team led by geophysicist Seth Campbell of the University of Maine surveyed the area. He explored some nearby caves.
Thing I've never been seen, probably.
And towed a ground-penetrating radar on a sled to identify perilous crevasses beneath the surface.
In here, we can show you what they look like. The way radar works is we're imaging layers in the snowpack below us. So we can see there's a crevasse here, and we can see there's actually a crevasse here as well.
Others were more obvious. Working on the edge of a glacier is dangerous business. A wrong step would be fatal.
I think we'll go around this one.
They also looked beneath the ice using another technique called seismic reflection, ironically often used by the oil industry to find places to drill. But in this case, they're making an underground map to ensure they are where the ice transitions from sitting on the rock to floating in the ocean, the so-called grounding line.
They detonated some small buried explosives akin to fireworks. Lizzie Klein is a doctoral candidate at Penn State.
When we set off that explosive charge, that creates a bunch of seismic energy that radiates down through the ice to the bed, to the bottom of your shelf. Any sort of change in material will trigger a reflection that comes back to us. And so this way we can see whether there's water or there's sediment or there's rock beneath the ice.
The reflections they recorded showed the ice, the seafloor, and a thin column of water. A bullseye, exactly where the team wanted to drill. They don't use drill bits here, just hot water, nearly boiling. The rig requires several aviation fuel-powered burners attached to a long spool of hose.
We see the drill rig, and then the hose goes down through a hole in the ground here.
Is it risky, ultimately, to the glacier itself?
No, because it's such a small fraction of the glacier. We're like literally touching 1/1,000,000% of the glacier.
When they finally got started drilling, a big storm blew in.
We really cannot see a picture visible at all. Stay in here for the day.
The team had to hunker down for 3 days. The timing was not looking good.
If we don't get the drilling started tomorrow, then we run into a whole series of problems. Basically, there's another storm coming in about 3 days, but we need 3 days to get the drilling set up and done.
But when the storm passed, the good weather held, and things fell into place quickly. After 36 hours of hot water drilling, they broke through the bottom of the ice to the ocean a half-mile beneath. They lowered in a remotely operated vehicle called Ice Spin, which provided some unprecedented images of the ice-covered shore of a glacier. Funded by NASA, the device was built by a team from Georgia Tech, led by astrobiologist Brittany Schmidt.
One of the things that we don't know very well is exactly how glaciers move and how the very base of the glacier operates. So when we get to see it right up close, right where it starts to hit the ocean, we're seeing the freshest material.
They collected sediment cores and dropped in instruments that measure water salinity, temperature, and turbulence. It turns out the water at this particular spot is very still. Aurora Bazinski is a grad student at NYU.
Since turbulence is below detectable levels, that means that there isn't as much mixing as potentially we would have expected. And so what that means is that the warm water is mostly staying near the bottom and not necessarily making its way up to the ice.
That might seem like good news, but for the first time, scientists have confirmed what they suspected. The ocean under Thwaites is warm, 3.6 degrees Fahrenheit above freezing, too warm for the ice to remain stable.
It's a sobering moment too, isn't it? Yeah. Change happens, and this looks like a potential case for change going forward that could be quite impactful. You can probably change air temperature over the next century, but the ocean is such a big, sluggish creature that in a way, when it's doing what it's doing, it's not the kind of thing we can engineer and stop very easily.
Before they left, the team buried 5 GPS stations across the grounding line. They will gather precise data about the glacier's movement and thickness over the long, dark winter. The MELT team plans to be back next year to recover that data and do more science. They hope this risky work at the edge of possible will help researchers make better forecast models, adding more facts to the growing fear. For the PBS NewsHour, I'm Miles O'Brien.
So that gives you a sense of what's involved with building a climate model is the collection of data that feeds the model. And currently in climate models, I'm not sure people are aware of this, we have a very good skill set in projecting global atmosphere temperature over the next century because we've been doing it for decades. Our knowledge and skill in the ocean is improving. However, our skill in the cryosphere or with ice is just at its early stages, and that's why so much research is happening in this area. And arguably, understanding ice is a far more difficult thing, I would argue, than understanding other parts of the climate system. It's such a complicated material. The end of that little segment also pointed to the fact that we were supposed to go back to Antarctica this year to collect our data, and that's now not going to happen because nobody's allowed in Antarctica. It's closed.
There's
So
no people, so why is it closed?
yeah, so the idea is, yeah, is typically you'd have 1,000 people there, but the idea is to evacuate one person from Antarctica requires the Air Force. And sometimes it takes weeks to arrive because of storms. So if somebody becomes ill, it could take them a long time to get them out of there, and other lives would be risked to get them out. So the idea is to just close it effectively, which is unfortunate for science. So let's look from today forward. I'm all about, given that we've seen climate change in the past and we've seen an accelerated change in the last century, what are we going to see over the current century? And to most people, I think now the concept of a climate model is well established. A model is how we have projections, scientific projections, and a model is made up, it's kind of a collection of all of our scientific knowledge. It's written in mathematical computational code and allows us to look at scenarios of the future. So interestingly enough, this person who most people have heard of, Isaac Newton, he developed the mathematical framework for climate, something called the calculus or calculus. And he actually did this during one of the previous pandemics, or certainly a large breakout of plague. And also he had to move to his farm or some farm to social distance. And with time to think, he came up with some very bright ideas. Another thing, and the same fellow, how can it be? But there's Isaac Newton again, and the laws of physics, which are how we interpret the climate system, are basically attributed to his findings. Of course, he built his work on other people. As he said, if I've made great progress, it's because I've stood on the shoulder of giants. And so he was quite a giant himself in terms of his contribution. So he really brought together mathematics and physics in a way that we could begin to understand the natural environment as well as other parts of the climate. So that brings us to the point where we are today, where we have mathematical descriptions of the atmosphere, the ocean, land, and ice. And the current paradigm is basically you make a grid of space and of time, and then you can have projective or predictive equations for each grid point. These models tend to be relatively coarse resolution, so you don't see a lot of detail in any area, like Abu Dhabi might be a single point, or the UAE might be a single point in such a model. Excuse me. And so as computers progress, no doubt that will improve, and there'll be better regional projections of climate. NYU Abu Dhabi, just a few years ago, had a very high-ranked computer, and computer rankings change all the time. So effectively, modern computers are just laptops like we all use, except there may be 100,000 of them connected together. And that's just to show you the scale of the computation. Is we want climate projections at a rate at which we can use them. If a climate model takes 100 years to make a projection for 100 years, clearly it's not very useful. It's all about having projections made in meaningful time that we can have advice for policy. So speed matters in terms of computations, and this is a big field of research. How do you compute something very fast? And speaking of which, the output of Newton's efforts and that of many other people are to look at scenarios going forward. On the right is a scenario where we will continue to have a high output of CO2 emissions. On the left, the opposite. And as you can see, as we go through the decades going forward, there are dramatic changes in the temperature on Earth. And I was recently asked by a person from the US Congress, kind of a skeptical person, but a very smart person, is why should I believe this simulation that we're looking at? And that person was from Florida, and I said, well, you have the hurricane forecast in Florida, and you rely on those forecasts to close Florida. And the person said, yes, we do. We completely believe in the weather forecast, the hurricane forecast is very credible. And then I pointed out, this is the exact same model. This is not a different model. Climate is the average of weather. And she got that point and took it on and understood that these are very reliable projections. This is science that we understand. We have a lot to go yet. There's a lot to do, a lot of physics, math, biology, chemistry, and all of the social sciences are needed to understand this problem going forward. One of the impacts of those changing temperatures, I mentioned about how sea level has changed in the last century. It's risen now about almost 30 centimeters. Really, the question is, for the coming century, what will be the projection? And the projection is all over the map, because the air temperature projection is all over the map, because we don't know what we're going to do with carbon dioxide in this century. Are we going to reduce it or not? And thus you see this uncertainty from a small amount of sea level to an amazing amount, something over 6 feet, which would wipe out a large part of the global coastline. And so this is a very serious problem that I think people are taking more and more serious all the time. So what do you do about that? Well, there's the thing called suffer, which is do nothing. And that's certainly a plan, right? You can do that. You can adapt. For example, you could build walls around your city or things like that. There's a lot of things you can do. In New York City, walls are being constructed between buildings to build kind of a natural defense. I think the UAE or Abu Dhabi will think of other strategies. But there's small cities can be protected. Large areas like the state of Florida, you cannot put a wall around Florida, or countries like Bangladesh. So there's a limit to what you can adapt. You can mitigate, which is becoming more and more effort, but probably bigger rewards. You can go to the source of carbon dioxide and change it. And then you can reduce the amount of CO2. However, each of these steps require more human input and more human cost. And I think there's a kind of a resistance at some level to doing more and more, when in part, some people are skeptical of this science. And in other part, people perhaps don't want to take action when they don't know if there's a certain outcome. But what I like, and it comes from a documentary that we created recently with a group of people, and some people in that, students and others, discussed this idea of prosper, which is a really interesting idea, and it's the one that made the most sense to me, which is you can do better than mitigate, which sounds like hard work and you got to struggle and you got to pay for it. It's like, no, you can prosper. You can create new technologies, new resources, new ideas that lead to you yourself becoming more prosperous and benefiting, and the world from benefiting. So sometimes I feel like it's phrased as a very negative, very heavy thing, climate change, we have to deal with it, it's a burden. Other people are beginning to look at it as an opportunity, for lack of a better word. And I think in that, I find more energy and more enthusiasm and a brighter future. The UAE government is one of the leaders in the world, actually. It actually has a Ministry of Climate Change, which is quite impressive, and a Minister of Climate Change, and a very broad climate change portfolio. And one of these, you can look it up on the web, this goal 13, I find very interesting, about actions and about how young people can be involved in climate and climate change. When it comes down to it, I think energy is the key word here. And what are we going to do? We know fossil fuels have a limited reserve of 100, 200, 300 years, some number of 100 years, and it's probably all gone. And we anyway don't want to burn it all because we possibly would have difficulty breathing. So given that, it's what is the new energy solutions for the Earth? The standard ones that probably it's some combination of this portfolio of solar, of wind, of nuclear, which also has some security concerns, and biofuels. And what's missing from this picture is some other thing that some bright student has not yet thought of, or some researcher in decades to come that will possibly eliminate all of these and will be a new idea. And history is filled with new ideas and game changers. And so we don't know what that is yet, but I'm sure it will show up in time to come. The question is, who's going to do this and how? And that really brings me to the main point for me of this sharing with students is the idea. Sometimes I think students think that this is a problem for someone else, or that they themselves cannot have an impact, that it's too big of a problem. Nothing could be further from the truth. Students and it's good to have a good intention to want to help the environment, and that's great. If you want to do it in a climate science way, then it requires rather extensive training in, for example, math and physics, or chemistry, or biology, or the social sciences, economics, etc., going into policy. All of these things, they take time to train people. And I'm very impressed with the students, certainly the ones that I teach at NYU Abu Dhabi. I can just see the change in the last decade of a much more active and positive group of students. They feel perhaps saddened or a little bit overwhelmed by the environment, but they also are very active in looking for solutions, and they are training themselves in the sciences in order to have an impact in the future. So I'm very much enthused and encouraged by that. So the summary of the talk is, first of all, climate is complex and at the same time it's delicate. The climate system is not something you can sit down and think through with your mind in the sense and just think about it. It's a very complex thing that we've learned through observation in nature. It's very surprising how the climate system works, but we go out into nature and we observe it and we learn how it works, and then we build models of it so that we can hopefully project the future. And what we're finding is that the climate system is incredibly delicate and is subject to change in ways that we don't yet understand. But we've seen it in the past, and we may see that change in the future. Going back to long time or deep time, variations in climate are huge and massive. Looking at more recently, the last 100 years, we are also seeing change. And what's somewhat concerning about the last century is that the rate of change of carbon dioxide exceeds anything we've seen in millions of years. So it has changed in the past, but it's never changed this fast. And so in the last millions of years. And so that's something that the climate system will deal with one way or another. And the final point is that the future is undecided. It's undecided because I don't know, and we don't know what's going to happen with carbon dioxide. What is the world going to do? Is it going to continue to output massive amounts of carbon dioxide? Are we going to change that? And and what we do with that leads to a planet that looks very different, one that has a higher sea level or not, a warmer atmosphere or not. There are lots of follow-ons from those decisions. And so that's where science begins to move over to policy. And policy is something that I'm not personally involved in. I think it's very important. And it's very important that scientists work to deliver to policy the best possible information. And that can only come from rigorous training and a lot of hard work going out into nature to understand how our planet actually works. And thank you.
Thank you, Dr. That was really exciting. I think I have a question, maybe talking back to your summary slide. So I have here Amna asking, so I think you already talked about how complex the climate itself, but she was asking, why is it like managing these changes? Why is it so hard? So what kind of things go into that climate that we cannot really manage this easily?
Yeah, so I guess the part that we can manage is the part that is, for example, human influence, which is, for example, deforestation, carbon dioxide, or other things in the environment. The amount of plastics now in the ocean is becoming very large. It's becoming more than the mass of the actual fish in the ocean. Yeah. So there are things we can influence about the planet. But there are things we cannot influence, and that is what is termed natural variability. And I think sometimes that confuses people in that in some decades it will be warmer in some areas than in other decades. So naturally, climate has changes in temperature and humidity and rainfall that are natural variations that are built into the climate system. You may have heard of some of these natural variations, something called El Nino in the Pacific Ocean.
Okay.
And in the North Atlantic Ocean, it's called the NAO, the North Atlantic Oscillation. So inherently, our planet on the short timescale has a lot of natural variability, but it also has some force change represented by us. And the two things are going on at the same time. I don't know if that helps answer your question, but I was trying to decipher or distinguish the difference between our influence and that of the Earth by itself.
Yeah, it makes sense. So we can do things, I guess, from our perspective when it comes to CO2 and plastic. And I mean, that could be as a personal level, but then policy here plays a bigger role when you're talking about full country, nations going in and changing that. Okay, so maybe I can ask you this question. So from perspective of today, we want, students want to actually study and make maybe a bigger difference. What kind of research they can contribute to? So you talked about your observational studies to help model the actual climate. What else, what other type of research could be done?
Well, one of the things that have changed in the last decades or so is originally science was a bit more in a silo. It was physics for physics and chemistry and economics. Everything was kind of separated. And what is really needed are students that are trained to be also much broader and able to speak across scientific boundaries, to not only understand chemistry or biology, but to also understand economics and the economic impacts associated with change. So there's this interdisciplinary thing, which is something that is important for students to be able to do. There's also the, at the same time, people need to have in-depth skills. We call it STEM, science, technology, engineering, and mathematics. So across all of these things, people need to be trained. And it's less about need to be trained, but it's really what it is that an individual really wants to do. There's so much opportunity for exciting science yet to be done. There's so many things to be discovered. And what's amazing about science and the broader thing is discovering something that nobody has seen before or understood before is just a lot of fun. And it's a detective game where you have to put together information with you and your colleagues. It's really a team game now. It's so complex, but there's nothing like it. It's just so exciting. It's not really a job. It's just a fun thing to do for your life.
I totally agree. I mean, just having the idea of you're the first person to actually discover something or see something and then contribute with that knowledge to everyone else, it's by itself is amazing. I think we have one or two more questions. Here we have Aisha asking, she thinks that planting maybe mangrove or other plants might be a good solution to reduce CO2. Do you agree to that?
At face value, yes. And like everything, when you dig into it, sometimes there's a negative impact of something. At face value, I would say yes. More plants taking up CO2 is basically a good idea, and so that's a step in the right direction.
Okay, so this question is quite, I think I was planning to ask us. There's Asma here saying, as a person, as an individual, what can I do? Any small actions maybe can help in reducing climate change.
Right. So just 1 second, something beeping. It's your watch over there. So at the individual level, anything from saving electricity, saving water, because water ultimately comes from electricity in many cases, desalination and whatnot, and the electricity comes from burning fossil fuels. So obviously the saying, one small action by several billion people has a rather large result. So there's that part. And at the other extreme, there are people who will decide to take on careers in climate and in areas that we haven't even touched on yet. There's avenues to explore that have not even been thought of yet. The limit on human imagination, there is no limit. So it's open. And again, I want to stress that I think sometimes students don't see the opportunity. They think it's for someone else, or that's not something I can do. It's certainly quite the opposite.
Yeah, I think today we have a lot of opportunities, whether in the UAE or outside the UAE. Maybe if it's something they're interested in, they should go and try it. Like, do a bit of research, see if this is something you can do. And you don't know, maybe that's going to be your passion going on from there. So I think we only have 3 minutes left. Maybe Dr. David, your last message to people who want to study this field, people who want to add in any final message to inspire people within your field.
Yeah, so I would say not to make too much drama of it. The Earth is potentially going into a very serious crisis. We're certainly having one with the virus at the moment, but looking beyond that, I hope, on a longer time scale, we're seeing a similar thing happening with the planet and the state of the environment. And there's no more real estate. There's nowhere to go. So if nothing else, in our own self-interest, we need to take care of climate and climate science. And again, it's very in-depth, and it requires a dedication of people to do it. And the young people of tomorrow are the people to do it.
Thank you, Doctor. This was a really exciting journey for this past hour. I really enjoyed listening to you, and I feel like I am now more excited to actually go and do more. Maybe I can, as a person, I can do more. I think with COVID-19, we stayed at home. We didn't go out. We saved a bit of CO2 from going out. I think we can do more now going out of this experience.
Yeah.
Again, thank you for your time. Really enjoyed this.
Okay, thank you, Amal. Nice to meet you. Thank
you, everyone. Please go through the link if you need the certificate, and we'll see you hopefully next week. Thank you, Doctor again, and goodbye, everyone.